Okay, so welcome to Thursday's lecture. We will be discussing the remainder of Ampere's law today, so that's going to be our primary focus. If you did not join us for the first 10 minutes of lecture, we showed a video that was a crash course in Ampere's law, so that link is posted on the Canvas page. You know, I've been trying to post the links to those videos here in the pre-lecture videos, so if you are not able to join us, you're still able to watch those videos on your own time. Before we get started with the lecture, I just want to remind everyone, so tomorrow there is a midterm. The scheduled time is 8 a.m. to 8:50 a.m. Eastern Standard Time with 15 minutes of upload. So I guess the official end time is 9:05 a.m. Eastern Standard Time. For those of you who are west of the GTA, I've asked that you fill out the time zone survey. So I have pulled the result of that survey. I think I did that yesterday on Wednesday. And I've adjusted the start times accordingly. So if you did fill out that survey and you are west of us, you should be starting at 8 a.m. your own local time, because writing a test before 8 a.m. I think is a little unfair. If you're east of Toronto, then it should be later in the day or later in the afternoon for you, so that shouldn't be a problem. And I think for those of you who are in Asia, whether it be Korea or China, then 8 a.m. our time would be around 8 p.m. or 9 p.m. your time. Again, it's not an optimal time, but it's not horrendous either. In the same way that 8 a.m. our time is not optimal, but again, it's not horrendous either. Okay, I would encourage all of you to maybe click on midterm number 1 here. Do that sometime soon. And this verifies for you your own personal start and end time. Again, your own personal meaning if you're west of us, that means I've accommodated and inputted the values correctly. If you're registered with accessibility, I've adjusted and inputted your values correctly. Stuff like that. So it tells you here that it's locked until a certain time. So if you're west of us, it'll be locked until a later time, right? If you're west of us, let's say you're in British Columbia, then it won't say 8 a.m. It'll say 11 a.m., right? Because 11 a.m. our time will be 8 a.m. your time. And then it'll tell you when it's due for the rest of the class, right? It's due at 9:05 for the rest of the class. But for you, you might have a different time limit. So like, let's say you're registered with accessibility or something and you get a slightly extra time. Your time limit would not be 65 minutes. Your time limit will be longer than 65 minutes. Hopefully you're all practicing with CrowdMark. We will be using CrowdMark for the rest of the test. We will only be using Canvas for the multiple choice and the fill in the blank portion of the test. I will say ahead of time, though, if you are in the small group of people that have a shifted time or a modified end time, CrowdMark does not allow me to sort of individually shift times. So when you do submit to CrowdMark and you are in this sort of shifted category, CrowdMark will think you are late. That's okay. Please understand that we will just cross-reference the submission time on CrowdMark with your allotted time listed on Canvas. And as long as you're within the allotted time listed on Canvas, you should be good to go. Okay. So I think those are all the announcements. Yeah. Also you have a tutorial today. So, you can practice circuits, capacitors, Ohm's law, stuff like that in all very, very relevant for your test as well. Okay, without further ado, I think we can just hop on over to the lecture. So I told you yesterday that usually when I teach this class in person, we have this equipment, it's very standard equipment, and I bring in this equipment and I show students that you absolutely can have a force on a stationary wire. And it kind of blows your mind, actually, because, these are things that we see in day-to-day lives. Like, we see wires carrying current all the time, but we don't see them moving or getting a thrust or experiencing a force. And that's largely because we don't walk around with a magnet in our hand. right? We just walk around without magnets. So, you know, even a current carrying wire without experiencing a magnetic field won't do anything. The whole point of this is it needs to be in a magnetic field. So it's sort of a natural phenomenon that we don't really get a chance to see very often, which means our brain usually has a hard time adapting to this new idea. So usually I bring in this equipment and I show students this in person so they can see it in person. However, the best I can do now is show you a YouTube video or some sort of simulation. So this is what appears to be a high school physics teacher. I can just sort of tell from the background, the lab benches and the computers, it looks like a high school physics lab. And there's a teacher here that has a very simple circuit. He hooks up a copper wire to a battery inside of a U magnet, and he uses his right-hand rule to predict kind of the thrust on the wire. So I think it's only about a minute long. So I think we're going to start with a review of yesterday's lecture by looking at this video, and then we're gonna move on.
So I have here a large magnet, south pole, north pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. I'll get this guy out of the way. And there you see it, floating there. Because now that I've reversed the direction of the current, current is flowing this way, magnetic field is pointing up, we expect an outward force. And that's what you say. Right-hand rule, simplified.
Okay, so very short video. The demonstration is no more exciting in real life than it was here. It was sort of anticlimactic in the video. It's sort of anticlimactic in real life as well. You know, I have a whole audience of, I don't know, however many students that are in the class, and they just see a little wire bend about 30 degrees, and you know, it's not very exciting to look at. There's no sparks or anything, but it really does drive home the point that a current carrying wire is effectively magnetic. You know, just like a fridge is magnetic. You can put a magnet on a fridge and put up artwork or whatever it is you put on fridges, a to-do list. So, you know, if you have a current carrying wire, it becomes magnetic. You can put a fridge magnet on it as well, and that would work. So anyway, just wanted to show you that. So here we are. We have left off. Yesterday we talked about a really cool application of both a combination of electrostatics as well as magnetostatics. We did mass spectrometers, or another, you know, you can call them mass selectors, either way. And you can use this as a tool to identify what particulate matter, an unknown substance, is based on its mass. Now, of course, the assumption there is the thing you're looking for has a unique mass. I mean, if two different substances have the same mass, then it can get a little bit confusing. But nonetheless, it's a really helpful analytic tool when you are looking for identifying a substance that is molecular. You know, you can't just look at it and be like, well, yeah, that's blah, blah, blah. So anyway, that's really cool. Now here, we did another example where we shot an electron through a parallel plate capacitor. And as we saw in assignment 1, it would obviously deflect. Depending on which side is the positive plate, which side is the negative plate. It'll either follow normal projectile motion downward like we see with gravity, or if you flip the plates, you'll see projectile motion but upward. which is no different. The physics is no different. It's just kind of interesting to look at with your eyes. And the premise of this question is, can we add an external magnetic field B such that this particle can pass through undeflected, meaning whatever upward force or downward force the electric field was pushing on this charged particle, the magnetic force would push equal and opposite, and allowing it to pass straight through. And you might be thinking to yourself, well, why is this useful? The answer is this allows us to be able to precisely control the path of a moving charged particle. So like particle accelerators, for instance. How do you think the particle accelerator keep the particle dead smack in the middle of the particle accelerator? And the particle accelerator is usually circular, right? So how do you think we get it to go in a circle? We need to be able to exert a force on this charged particle in a very precise, controlled fashion. And we do that using a combination of stationary electric and magnetic fields. And then we can make sure that the particle goes where we want it to go. So it's a very useful thing. So we're going to finish the topic of magnetostatics by talking robustly about Ampere's law. I've already sort of mentioned the introduction of Ampere's law previously, but now we're going to really, really delve deep into Ampere's law. So just context, storytelling for a second. Again, partially review for tomorrow. We used Gauss's law to govern electrostatics. And Gauss's law we used to relate the source of the E field, Q, charge is the source of the E field, we related the source to the field itself, E. So Gauss's law you see here, what happened? Draw, there we go. We related the source Q to the field E. And the idea behind Gauss's law is we use Gauss's law in conjunction with F equals QE to obtain a formula first for the electric field E and then F itself, right? So our end game with the previous chapters was to obtain and quantify a value and a formula for the electric force. And we did that through Gauss's law. We used Ampere's law in exactly the same way. So the story you told yourself when you're practicing with electrostatics questions and you sort of got into a rhythm where you needed to know, well, what's the electric field due to an infinite sheet? Okay, you set up Gauss's law, you find E, multiply by Q, find F, okay? It's the same idea now with Ampere's law. If you are ever in need of finding the magnetic field B, it's the same story you're telling yourself. Just instead of Gauss's law, you're using Ampere's law. You use Ampere's law to relate the source of the magnetic field, which is a moving charge, it's a current, and you use that to find B itself. So you use Ampere's law to find B, and then once you have B, you use the relationship between the field and the force to find the force. So it's the same sort of idea. So here's an example of how you would use Ampere's law. So again, mostly the same story as we did with Gauss's law. This was sort of summarized in that pre-lecture video I showed you. So again, after the lecture, if you missed it, you can go back and watch it with the link that I posted. So here, what we do is we have a long straight wire, and we have an idea of what the magnetic field might look like, but we don't know the formula for the magnetic field. In fact, even presently, we have in lecture, we've talked about how the magnetic field due to a long straight wire will look something like this. It'll look circular in concentric circles. And I think it's obvious that you can think to yourself, as you get farther away from the wire, it gets weaker, obviously. I don't know why I didn't change color there. There we go. So as you get further away, it's understandable that it would presumably get weaker. And then as you get closer, it would become stronger. That's a bit of an assumption. Now, one thing we do know for certain is that, let me list this here. This is a small assumption. At the moment, we can't really back that up. In fact, we saw with an infinite sheet that it doesn't matter how far away you are, the electric field is a constant value. So, you know, it's a bit of a leap of faith, I guess, to say that when you get farther away from a wire, it's going to be a weaker magnetic field. So we don't even have to focus on that at the moment. But what we do know for absolute certainty, we do know 100% that along each circle, the B field is constant. That's what we do know. Now, it might be constant even with outer circles as you get farther away. It might be, we don't know. Or it might not. If it's not, we don't know if it follows inverse square law. We don't know if it follows the negative exponential. We don't know, right? That's really what we're trying to find out. So once we have a sort of picture in our head of what the B field might look like due to an infinite, just a straight wire, whether it be infinite or not, what we do is we use Ampere's law in a very similar fashion to how we may have used Gauss's law. Let me just insert some blank space here. Okay, so here, what we do is we say, okay, Ampere's law is the integral of b dot dx dot, it's not b times dx, it's vector b dot product with vector dx times mu naught times the total enclosed current. Now, we briefly discussed this sort of vector nature with flux and Gauss's law. So really what this is saying is there's sort of three aspects here. There's the strength of the magnetic field. There's the angle, you know, in the dot product, cos theta, right? There's the angle in the dot product. And then there's sort of the path itself. And vector calculus is very complicated, and despite what you might think of physicists, we really do like to avoid the math as much as possible. You know, as good as we are at math, we do not like doing it. That's, I guess, the main difference between us and mathematicians is we use math as a necessary tool, not out of pleasure. So we will try to sidestep the math as much as humanly possible. So let's think about this. In an integral, to simplify the integral, you can pull out or factor out constants. So let's see if we can create an Amperian loop, which is equivalent to a Gaussian surface, a closed imaginary loop that we're integrating over in such a way that along this imaginary loop, the B field is constant, the theta is constant, and that we know what the path itself is. Because if we know all of these things, we can easily factor them out, and then Bob's our uncle. So here, I think to myself, okay, where is my Amperian loop? Where can I draw a path, an imaginary path? Where can I draw a path in such a way that the magnetic field is constant along that path? That's what this green note is for. So if I draw an Amperian loop, red dotted line here, this is my Amperian loop, then along this imaginary line that I'm integrating over, my B field is constant. In addition to that, the angle between the loop and the B field is also constant. It's 0. Cos of 0 is 1. They mentioned this in the video as well. So if you're going back now to watch the video after the lecture, hopefully this makes a little bit more sense. So now, if I pick the red dotted line to be my Amperian loop, what I get is I get the ability to factor out B cos theta, and now I simply just get the integral of dx and this equals mu naught times the total enclosed current. So then you have to ask yourself, although the path that we chose is helpful in that it makes B field constant, we can factor it out. It makes angle constant, we can factor it out. We have to ask ourselves, really, is this useful in that we know what the path is? Same thing with Gaussian surface. I could have picked an oblong shape. It doesn't mean I know the surface area of the shape. Here, do I know the total path that I've traveled? If I pick an oblong shape, I'm not going to know the perimeter of an oblong shape. Luckily here, we picked a circle. We know the path of a circle. The path of the circle is simply, it's simply 2 pi r. And here, no more integral. Yay! So what we can do is we can just solve for b. And again, I'm making note here that cos theta will be equal to 1 because the angle is equal to 0. So this here is the B field. That's not a B, or that's not a D, due to a straight wire. And again, yes, this is a formula. You could memorize the formula. I don't know how many times I have to say this in physics. I do not recommend approaching your physics education by memorization. I know students come into physics having been quote unquote trained by the academic system to like memorize material, regurgitate it for the test. That does not work in physics. You really, there's just way too much to memorize for any human brain. You need to understand, there's too many facets. You need to understand the story that's happening in order to perform well in physics. So this is why I'm going to great lengths in lecture to sort of explain where these things come from to help you recreate them as you need them, because there's just too much to memorize otherwise. So this is a very well-known formula. You can look it up in a textbook, you can look it up online. This is where it comes from. It comes from Ampere's law. In the same way that Coulomb's law, KQ1, Q2 over R squared, is a very well-known formula, but I showed you where it comes from. It's a result of Gauss's law. So otherwise, there's just too many formulas, too many equations, too many situations to memorize in order to do well on any evaluation that you need to do by yourself, right? Without asking friends or looking to Google. If you had to do it by yourself, there's too much to memorize. You have to start understanding the concepts. So here we go. This slide is just a summary, a typed summary of what we just went over by hand. So in case you don't like my handwriting or something, you can look back at that slide. And there's the conclusion there of the integral and the division. So again, if you don't like my handwriting, you can look at the slide there. Just a brief side note, mu naught, you might be asking yourself what mu naught is. Well, if you recall with Gauss's law, and you'll notice here, every time I say Gauss's law or Ampere's law, I always pause to take time to write down the equation for you, because the more times you see it, hopefully the easier you will be to, it'll be for you to use it. So you'll recall with Gauss's law, we had epsilon naught, the permittivity of free space. That was a measure of how easily the electric field can propagate through that medium, whether that medium be a vacuum or air or glass or concrete, right? Well, now that we have a different field, we've got a magnetic field, mu naught is called the permeability of free space. And permissivity, permeability, I know, they sound very similar. I don't really care about the actual English word of what they're called, as long as you understand what the symbol represents. Mu naught is analogous to epsilon naught. Instead of for electric field, it's for magnetic field. It is the ability the magnetic field has to propagate through that material. So if you're talking about an electromagnetic wave, if there's a wave that has both an electric component and a magnetic component, then obviously you will need knowledge of both epsilon and mu in order to complete the analysis. Now, epsilon had this weird complicated number. mu naught is actually slightly more conducive to working with. It's actually 4 pi times 10 to the negative 7. So that's actually helpful because pi comes up quite a bit in our calculations. So when you substitute mu in, you often are able to cancel the pi, which is kind of really cool. Okay, so it's still early in the morning, and I kind of want to see how awake you guys are. So I am going to launch a poll here. Launch a poll, there we go. So you're going to see a poll come up on your screen. And I'm going to shrink this slide so you can see it on your screen. So here's the question. If the currents in these wires have the same magnitude but opposite directions, what is the net magnetic field at point P? So there's 2 wires here. Wire 1, oh, that's in black. Let me try red. Wire 1, wire 2. And the X means the current is going into the page. The dot means the current is coming out of the page. What is the net magnetic field at point P? Is it arrow 1, arrow 2, arrow 3, or arrow 4? Oh yeah, the Jeopardy music. See, I say that every time. This would be a great time to have the Jeopardy music. Okay, so 13 of you. Okay, well, for the interest of time, I think we're going to end the poll. So it's interesting. Let me share the results. So here we are. We have 50% is the Democratic winner for E. The B field is 0 at point P. However, a very close runner-up with 43% of the vote is C. C being direction 3, which is straight downwards. So if we had to analyze this, let me stop sharing the results for a second so you are able to see your screen again. Let me make this slide a little bit bigger. Okay, so use your right hand rule, thumb in the direction of the current. So I'm going to put my thumb into the page and I wrap my fingers in the direction of what the magnetic field would be. So at point P, then my fingers are going to look something like this. So the magnetic field is going to be clockwise. Oh, I just right-clicked. Clockwise from the left-hand wire. So at point P, that means the B field is going to be pointed down at that one specific point. Now, due to the other wire, right-hand rule, thumb out of the board, and your fingernails now wrap in the other direction. So your B field is going to be sort of pointing down and on an angle like this. And you see here when you vectorially add these 2 vectors, you see how they have perfectly canceling horizontal components, but they have constructively adding vertical components. So your net B field is going to be pointing straight down. So your answer here is actually C. So I guess, although Democratic voting usually is good for political issues, because there is no right answer in politics, it's really whatever the people prefer. This is why we don't do democracy in science, because science actually does have an objectively correct answer. And I think there's a famous quote by someone famous, I don't know who, but someone says, well, science, the truth or science is not subject to your opinion, something along those lines. I'm paraphrasing. So here the answer is C and not E. So even though the majority of you voted E, you know, it's good that we did this vote then, because then we can clear up that misconception. Okay, now that we've sort of got that sorted out, let's do an actual worked numerical problem. So a straight wire, or sorry, a straight horizontal length of copper wire is known to have a current of 28 amps. Wow, 28 amps is incredible. Just for the record, you have you probably have about 10 different circuits or so in a house. Maybe, well, maybe more like 20. If you look at the circuit breaker in your house, you'll notice a bunch of switches, and most of the switches aren't used. They're not necessarily hooked up to anything. They're just kind of there for future use in case you want to install pot lights or something like that. But let's say you have about 15 circuits in your whole house. That includes your furnace, your air conditioner, all your plugs, all your lights, everything. Each circuit, usually in modern households, has a threshold, a highest amount of current of about 15 amps. So this one wire alone is carrying 28 amps. That's almost twice the allotted amperage in a household circuit. So that's an incredibly high amperage, just so you know, just for context. Because I know if you don't have any personal experience with current, you might think 28 amps is a small amount or something like that. So I'm just telling you, for the record, 28 amps is quite a large number of amps. By the way, side note about amps, people think voltage kills you. High volt, danger, high volt. No, voltage doesn't kill you. I think I've talked about this before. When you shock yourself opening your car door, that's thousands of volts that you've touched. It might hurt you a little bit, like, ow, that shock hurt me, but voltage doesn't kill you. Current kills you. Amperage will kill you. I'm going to ask facetiously, does anyone know how much current it takes to kill a person? It takes about something on the order of magnitude of milliamps. Milliamps, 10 to the minus 3 amps. That's all it takes. Now, if you put a milliamp through your finger, that's not going to kill you. It has to be a very targeted milliamp. So targeted meaning across the heart. If you have a little bit of a current, even a little bit of a current through the heart, it'll throw the rhythm of the heart right off. It'll give you a massive heart attack and it will kill you. So current is what kills you. So 28 amps will not only knock you flat on your bum, it'll probably kill you pretty quick. So very dangerous current. Anyway, side note, back to this. Horizontal, so current. Oh, I'm writing in red. So I'm gonna start writing down my givens because words confuse me. What are the magnitude and directions of the minimum magnetic field needed to suspend the wire? So the magnetic field equals this. We're also given a mass density of 46.6 grams per meter. Okay, so what's going on here? We have a wire, a heavy wire, presumably, because it's carrying a large current. So it's quite heavy, and gravity will pull it down. The question is saying, there is a current in the wire, therefore the wire itself is producing a magnetic field, obviously. What is the amount of B field we need to add externally to result in a magnetic force on the wire that combats the force of gravity? So if we were to draw a free body diagram of the wire, we're looking for a magnetic force up to combat the force of gravity downward. So there's my free body diagram. And after a free body diagram, we always go to F net equals ma. And given the context of the question, our desired acceleration is going to be 0, right? I don't want this wire to be accelerating up or down. I just want it to be like stationary and levitating. Actually, this is how levitation works as well, by the way, magnetic levitation. So here, we keep going. So the net force is going to be FB minus FG, and that's going to equal 0. And this is going to be FB equals FG. So there's our equation. Now we have to sort of expand it a little bit. So what is my magnetic force? Well, is this a force on a particle, or is this a force on a wire? So it's a force on a wire. So we use ILB, and the force of gravity is a little bit more complicated. We know the force of gravity is mg, but the question really is, well, what is m? What is m? We don't know what m is. We don't know the mass of the wire. Obviously, the longer the wire, the more mass there is. The heavier it is, the larger the m, the larger the force of gravity. So we don't know what m is, but we can compute m in terms of its length. So we say the mass is going to be the density of the wire multiplied by the length of the wire. So if it has, let's say here, 46.6 grams per meter, and it's 1 meter long, then the wire is 46.6 grams. If it's 2 meters long, then it's closer to 100 grams, right? So that's, you just multiply the density by the length, and then you get the mass. So here we get the equation, ILB equals rho LG, and you can cancel the L. So it doesn't matter how long it is, right? Because you're applying a force per unit length anyway, so it doesn't matter how long it is. And then we're solving for the B field, so B is going to equal to the density times G divided by the current. And there you have it. So I suppose we could have done that question yesterday. So I guess that was just sort of a review warm-up. Okay, here, this is more related to Ampere's law. So the video we mentioned before the lecture, the pre-lecture video, again, link is posted if you want to go back and watch it. They talked about the force between two wires. The force between two wires is actually really interesting. It's something we don't normally think about. That, you know, if you have a moving charge generating a magnetic field, it can feel a magnetic force because external magnetic fields can interact with that induced B field, right? Well, two wires, if there's a current in them, not only produce its own magnetic field, which means other magnetic fields can exert forces on them, but that magnetic field can be used as an external magnetic field for the other wire. So what happens, for instance, as an example, is let's say we take current 1 here, current 1. Use your right-hand rule, thumb in the direction of the current, so point your thumb up because it's pointing up the screen, and then grab the wire with your right hand and your fingernails point in the direction of the magnetic field. So your fingernails are going to look something like this. And the B field, with concentric circles, the B field at a location directly to the right of it, we're going to get these sort of concentric circles, and it's going to point, the B field is going to point into the page at that location, okay, at that location. Well, that means we can calculate the force on wire 2, and that's going to equal ILB. Well, we use our right-hand rule. We know the B field, the external B field, at the location of wire 2 is into the board. Okay, so I don't care which right-hand rule you use. You can use your physics gangster sign right-hand rule, or you can use the give me money right-hand rule. I'm going to use the give me money right-hand rule just because I contort my arm less that way, so that's what I prefer. So fingernails into the board, my thumb points upward in the direction of the current, and the palm of my hand, if you can see the lecture video instead of the shared screen, the palm of my hand is facing to the left. So that means this wire will feel a force to the left. And similarly, we can repeat this analysis, but for the other wire, right? If we think, okay, well, wire 2 is the one generating the B field because it is also generating a magnetic field, then using your right-hand rule, you're going to get a B field that is like this. And at the location of wire 1, at the location to the left of wire 2, you're going to get a B field out of the board at a location directly left of the wire 2. So again, if you want to look at the force on wire 1, that's going to equal ILB, ILB again. And again, right-hand rule, fingernails out of the board, fingernails out of the screen, pointing at you, because that's where the magnetic field is pointing. The current is up, and the palm of my hand is facing, as you can see in the camera, is facing to the right. So that is why that pink arrow there is labeled to the right. So interestingly enough, two wires that are side by side that carry the same current in the same direction will actually attract each other. And that sort of makes sense if you think about it. In fact, that actually almost has to make sense, because if you have two currents in the same direction, then what if you just sort of merge these wires together and just kind of like blend those two wires together? Well, that's no different than having one current in your wall with one wire. It's not like the magnetic field in the wire makes the wire bust apart, right? So it almost makes sense logically that two wires that have the current in the same direction have to attract each other. Otherwise, one wire would try to break apart. You know, if you slice a copper wire in half, then you're going to get two smaller copper wires. That doesn't happen in nature. You know, when you make a current go through a wire, it doesn't bust apart. If you have wires with currents in opposite directions, then the opposite is true. They will repel each other, right? Now, I don't know if any of you have done this. I've done a little bit of electrical work in my home over the years. I've changed some light switches, I've changed some wall sockets, and I do not recommend that unless you know quite a bit about electricity, because you can get very badly hurt or cause some sparks, which could also hurt your eyes, and you could go permanently blind if they hit in the wrong spot. The sparks could start a fire as well. So don't do this unless you are confident you know the physics or you are trained as an electrician. But I attempted it because I know the physics and I felt confident I could do it safely. And what I was able to do is, when I hook up the new light switch or the new plug, before I put everything back in the wall, what I do is I turn the circuit back on downstairs, just to make sure I wired it correctly. I don't want to put everything in the wall and realize it doesn't work and be like, oh, I got to take it out again. So you always kind of test it first. And what you do is, if the light switch is on, like set to the on position, so when you turn the circuit on, the light would immediately go on. What you notice when you turn the circuit on sometimes is if there's a load in the circuit and there's current immediately flowing through the wires, you notice it kick, which is kind of really cool. So if you have like a receptacle kind of hanging out of the wall and you have like a space heater plugged into it and you turn on the circuit, you'll notice the wall plug will actually rotate. It'll actually give it a little bit of a kick, kind of like what we saw in that video, that 1 minute high school teacher showing you. There's a bit of a kick there. And that kick is a result of two wires repelling each other because they're in close proximity. So that's kind of really cool as well. Here is a past midterm question, not from one of my midterms, from just a different instructor, but nonetheless, it's a past midterm question. That text is really small. Maybe I'll leave it zoomed out here so we can see it. So we'll very quickly do this question. Maybe I'll set it up for you and I'll let you finish it on your own, but the setup should be the hard part. And once it's set up, the rest should be fairly easy. So the premise we have here is we have two wires that are hanging from a common point on the ceiling, and by some sort of thread, not wire, some sort of thread. And the wires themselves are carrying currents in opposite directions. So we know from the previous slide that that's going to repel each other. And they repel each other. And what we observe in real life is that the threads are at an angle of 15 degrees. Okay? So the question is pretty much, what is the current in each wire, given the set of variables that we see here? So again, this is some sort of forces question, because the system is in equilibrium. There's a force kind of pushing them apart, causing a sort of equilibrium angle, 15 degrees. So it's a forces question. Let's just draw a free body diagram. So let's draw a free body diagram of the wire. So this is a free body diagram of the left wire. If you want to draw one of the right wire, knock yourself out. So here, the current's going into the page. What are the forces acting on this wire? Well, let me just label this as a free body diagram. So the forces is that the tension is sort of up on a bit of an angle. And I have gravity pulling down on this wire. And I have one other force that I'm missing because right now, as I've drawn it, the vertical part of tension balances gravity, but the horizontal part of tension is unbalanced, right? So there has to be something balancing the horizontal component of tension. So the thing I'm missing here is there is inherently some sort of magnetic force pushing to the left. So there's my free body diagram. And then we mosey on over to F net equals ma. And we are in equilibrium. So the acceleration in this system is 0. And we note here that it's two-dimensional. So there's an x and a y. So we have to do F net equals ma twice. So let's start with y just because we got to start somewhere. We have to start somewhere. Let's start with y. So F net y is equal to 0. Looking at my free body diagram, what forces act in the y direction? Well, I've got tension in the y direction, and I've got gravity, 100% of gravity, and that's it in the y direction. So their sum must equal 0. And tension in the y direction, well, what do I have here? I have this angle. The angle it makes with the vertical is not 15. You'll notice in the diagram, 15 is the total angle between the two wires. So this angle here is actually theta over 2. It'll be 7.5 degrees. Now, I don't like plugging in numbers because you could easily say, well, what if it wasn't 7.5 degrees? What if it was 9 degrees? So the total angle was 18, right? Well, then if you plug in numbers, you have to go back and recalculate everything. It's just really annoying. If you leave everything as a symbol or as a variable, then it's quite simple, right? You're just changing the final answer. You're not having to go back to recalculate and rearrange all your equations. So here, if I'm solving for tension, this is going to be tension in the y direction. So this is going to be T cos theta over 2 equals the force of gravity. So tension is going to equal mg over cos theta over 2. All right, I know we weren't asked for tension, but we can solve for it because we have m. Well, we sort of have m. We've got theta. We may not have m, but what do we have? Right here, the mass per unit length is 0.05 kilograms per meter. So we have the density, the linear mass density of the wire. So as we've done before, we can find mass that way. So we can go here and say this is going to be rho Lg over cos theta over 2. So we can numerically solve for tension if we want to. We can obtain a value for tension. Not that we want to necessarily, but we will need to swap it out when we look at the x component. So when we say F net in the x direction, that's going to equal 0. In the x direction, we have tension sine theta over 2 minus the magnetic force is equal to 0. And there's that pesky tension again. So we actually know what tension is. So we can plug tension in for this. So tension is going to be rho Lg. Then we're going to get sine over cos. So this is actually going to end up being tan theta over 2. And this is going to equal the magnetic force. This is the magnetic force on the wire. So this is going to be the current in wire 1, L, and this is going to be the B field due to the other wire. ILB, B being the external B field. So the external B field is the B field generated by this second wire here. Okay, so let's keep going. Rho Lg tan theta over 2 equals I1L. And B2, what's the magnetic field equal to from wire 2 at the location of wire 1? Well, it's the magnetic field, as you see in the diagram here, it's the magnetic field due to a straight wire. We've just used Ampere's law to determine what that formula is. That formula was mu naught current 2 over 2 pi r. Now, in this particular example, the current in both of the wires is the same as each other. So I1 equals I2 in this case. So in this situation, current 1 equals current 2. In this case, they don't have to. You could easily have two neighboring wires that are carrying different currents, right? There's nothing against the laws of physics that says two wires beside each other must carry equal and opposite currents, right? So, but in this case, they do. So let's go and simplify some things. Okay, so we're going to get rho L G tan theta over 2 equals I squared mu naught over 2 pi. And what is R? R is the distance between wire 2 and wire 1. That's the distance. Now, we do know in the question that this wire is 1.2 meters in length. So, using the hypotenuse, we can actually calculate this distance. So in this diagram here, we can actually calculate this distance. That's going to be half of the radius between the two wires. We can calculate this distance by saying L being 1.2 meters, L sine theta, and then we have to multiply, and then we say R equals twice that distance, right? Because L sine theta is only half of the distance between the two wires. So to get the full distance between the two wires, it's twice that amount, okay? So here, down here, we can say the R value is going to be 2L sine theta. Oh, it's the pen is acting weird toward the bottom of the screen. Okay, so I would say now we pretty much have our answer. We were asked to find the current in these wires. So now I can isolate for current because I think I have everything else. Here we're going to have rho L. No, L was canceled. I don't know why L was there. That's my apologies. Rho. Well, let's put all the constants first. Then we're going to have what? 4 pi. There's 4 pi. Any other constants? No. Rho GL sine squared theta over 2 over mu naught cos theta over 2 square rooted. Okay. And interestingly, as I mentioned before, mu naught is 4 pi times 10 to the minus 7. So if you want, you can actually just go back and substitute 4 pi times 10 to the minus 7. And you see how the 4 pi in the numerator will sort of cancel. So if you wanted to, now if you don't want to, it's still fine. You're not going to be marked wrong if you don't do this, but just as a fun little exercise, if you do plug in mu naught, then you are going to see something slightly simpler. You're going to get this. Okay, So 4 pi times 10 to the minus 7, the 4 pi's cancel, and the 10 to the minus 7 goes up on the numerator and becomes 10 to the positive 7. Okay. So there you go. There's your equation for current. That is the that's how you could reverse engineer the current in the wire if you observe two wires that are 15 degrees to one another, suspended from a string that you are able to measure in real life to be 1.2 meters. Okay. Okay, moving on. More about Ampere's law. Okay, Ampere's law, like Gauss's law, is, oh, what happened? Ampere's law, like Gauss's law, is always correct, but not always useful. So remember, we had 3 assumptions for Gauss's law, right? For Gauss's law, assumption 1 was we needed to pick a Gaussian surface where the E field was constant at each point along the surface. We needed to pick a Gaussian surface where theta was constant at each location on the surface. And then the third assumption we had for Gauss's law was that we know the surface area of the Gaussian surface, meaning it was a shape whose formula for surface area we knew. We have similar things for Ampere's law. We have similar assumptions. One, we had to pick an Amperian loop, a L Amperian loop, where the B field was constant. 2, we had to pick an Amperian loop where theta was constant, okay? And then 3, we had to pick an Amperian loop where we knew the perimeter. Where we knew the perimeter. Okay, so if you can manage those 3 things when using Gauss's law or Ampere's law, then it's a very useful equation. As I've explained with Gauss's law, you are going to get the same answer regardless of what shape you pick. That's true with Ampere's law as well. But we're only human. Humans have limitations. If we pick a different shape for Gauss's law, or we pick a different shape for Ampere's law, we as a human may not know enough math or have enough patience to sit there and do the math to get that answer using that other shape. Now, that doesn't mean a computer can't, for instance, or an overzealous mathematician who just wants to do it the hard way for some strange reason, which wouldn't shock me knowing mathematicians, but anyway. Just because they're not always, okay, so Ampere's law and Gauss's law, they're always true, they're not always useful. Here's what I mean by that. We've talked about a scenario where you take, wow, that was quite a scroll. I don't know what happened there. So we've already talked about the magnetic field due to a current loop, one single current loop. We've talked about how to think about the magnetic field. We talked about how to relate the magnetic field due to a straight wire and how you can bend the straight wire into a loop and you can predict its sort of B field that way. Here we have a very strong north pole. Here we have a very strong south pole. Let's see if we can use Ampere's law to come up with a formula for this. And the answer is we can't. Here's why. We are not able to satisfy those 3 assumptions. Let's try to naively pick a circle, as we did with a straight wire, for our Amperian loop. So if we pick this red Amperian loop, then we will be integrating the magnetic field across this red loop. Well, let's see. Is the magnetic field, assumption 1, is the magnetic field B constant everywhere along this loop? Well, the magnetic field here, we know, is quite strong. We can see that in the diagram. There's a lot of magnetic field lines at the center of the loop. outside the loop. Is the magnetic field strength the same outside the loop as it is inside the loop? No, it's not. So the magnetic field strength along the red Amperian loop is not constant everywhere. So right there, right, boom, right out of the gate, one of the three assumptions doesn't hold. Now, in addition to that, assumption 2 also doesn't hold. The angle between the B field and the Amperian loop is not constant. Here, the angle is equal to 0, but here, for instance, the angle is approximately equal to 90 degrees, right? Because the loop will sort of rotate, and the B field is going sort of straight. So it may be not exactly 90, but it's close to 90. So the theta between B and the path is also not constant. So 2 of the 3 assumptions are false. However, the third assumption holds. Do we know the circumference of the circle? Yes, it's 2 pi r. So you're thinking to yourself, Mark, okay, then fine, don't take a circle. Take a different shape. Okay, I'm right on board with that idea. Let's actually take an Amperian loop that traces one of those field lines perfectly. That satisfies theta. The angle between B and the path is always 0. So that satisfies assumption 2. Okay, beautiful. Does it satisfy assumption 1 though? Is the B field the same strength here as it is here? No, it's not. So this would not satisfy assumption number 1. It also does not satisfy assumption 3. What is the perimeter of that shape? Well, it's not circular, so it's not 2 pi r. It's not necessarily elliptical either. It's something. It's what we would consider oblong. I mean, it's maybe not what the average person would consider oblong, but mathematically it's oblong because we don't know what it is. So humans are not able to use Gauss's law. That doesn't mean Ampere's law. That doesn't mean Ampere's law is wrong. It just means it's not useful. Now, how do we obtain a formula then? Well, if you were in Physics 147, the calculus-based physics course, or let's say Physics 152 downtown, they would introduce some calculus, and there's something called the Biot-Savart law, which is equivalent sort of to Coulomb's law for magnetism. And they would integrate Biot-Savart law and get an answer that way. However, those are details that are beyond the scope of an algebraic-based physics course. So beyond mentioning kind of what it is, we will not talk about it. However, I will talk about the end derived result. The formula you get from Biot-Savart law is mu naught I over 2 pi r. Now, r is not the distance away from the loop, okay? R is the radius of the loop itself. So I cannot stress this enough. R is a constant. Okay, it's the radius of the loop. It's the radius of the loop itself. This is not to be confused. Not to be confused with if you have an infinitely straight or a long straight wire. We know the magnetic field will look like this. And we just got finished telling you that the magnetic field is going to be mu naught I over 2 pi r. Okay? Now, if you look at the similarity between these two equations, it looks like the only difference is pi. That is not the only difference. Huge difference. Big difference. Okay? This capital R is the radius of the loop. It's a constant. It does not change. This R is a variable. This R represents how far away you are from the wire. You could be 1 centimeter away, 10 centimeters away, a kilometer away, okay? It's a variable. This r is the radius of the loop. So what we've calculated here is actually, let me just zoom in here as well. What we've calculated is, wow, this does not want to scroll. We have calculated the magnetic field at the center of the loop, nowhere else. As you can see, it's because it's a variable. The magnetic field out of the loop is different than the magnetic field in the loop. And if you look at this equation here, mu naught I over 2r, those are all constants. Mu naught's a constant, the current in the loop is a constant, 2 is a constant, and the radius of the loop is a constant. So that's a constant value. So what we've solved for here is actually the B field at the center of the loop. Okay? So although the variables in those two equations look the same, mu naught I over 2 pi r versus mu naught I over 2r, they look the same with the difference of pi. They could not be more different. I mean, I guess they could be more different because they both represent B fields, so there are similarities. But given that, they're different, okay? They're describing different things. Okay, we're running out of time slowly, so I'm going to skip that question. It's just a polling question. So that video, the pre-lecture video, that was only 10 minutes, less than 10 minutes long, it was 8 minutes long. They did a whole crash course in what we were going to do in the 2-hour lecture. So we're slowly getting there. Now we're on to solenoids, or a coil. So first, what is a coil? What is a solenoid? All that is many loops that are in close proximity to one another. That's what a coil is. So you can see this here. We have one loop, and we analyzed one loop. We analyzed one loop previously. And all a coil is when you have multiple loops that are sort of pushed together in close proximity. Okay, so kind of like a spring, sort of like a spring, but if you run a current through a spring, sort of. It doesn't have to be a spring. It could, it could just literally be wires wrapped around, wrapped around, wrapped around, wrapped around. Okay, so let's analyze this. Let's analyze this. We know what the B field. I'm just trying to zoom in here carefully because if I do it too fast, it jumps around on me. Okay, there we go. So now it's most of the screen. We know what the B field looks like due to a single loop. We've just got finished kind of reviewing that. So picture the B field due to a single loop, but next to other single loops. We already know the B field due to a single loop has a very strong B field at the center of the loop. And if you put multiple loops in close proximity, then the strong center gets elongated, right? So the strong center, instead of coming out and then diverging right away, as a single loop would, it continues on. So you get a really strong center, and the field lines kind of go straight through the middle of the coil here. Kind of like, I don't know if you play Mario Kart, but if you play Mario Kart and you hit like one of those boosters, it's like hitting a booster, then a booster, then a booster, and then a booster. You end up going really fast. That's what's happening here. You get the B field strong at the center of one loop, and then it just goes through many strong loops. So it boosts it right in the middle. And then after it leaves the last loop, then it wraps around this way, right? Because all the magnetic field lines have to come home eventually, right? Don't forget Gauss's law for magnetism, integral of B dl is equal to 0. So that means the loops have to come back home. Now, this is interesting because this looks exactly like this looks exactly like the magnetic field for a bar magnet. That's so cool that you can actually create a physical coil using wire, and the magnetic field that that coil will produce is in every way the same as a bar magnet. And a bar magnet is a permanent magnet. There's no current running through a bar magnet. And it generates a constant B field like this. Here, as long as there's current through the coil, it will generate the same magnetic field as a bar magnet, which I think is mind-blowingly cool. This is exactly what we call an electromagnet. An electromagnet is a magnet. For all intents and purposes, it's a bar magnet. It behaves like a bar magnet. It's got the same magnetic field as a bar magnet, okay? So however you think a bar magnet will behave, this coil will behave in exactly the same way. And it's called an electromagnet because it's generated with electricity, like with a current. So it is an electromagnet. Now, we have a new situation, just like with Gauss's law. We had parallel plate capacitor, Coulomb's law, infinite plate, like a single infinite sheet. We use Gauss's law. Here we have a new situation again, so we try to use Ampere's law. Remember what I said about Ampere's law? If you have a new situation, use Ampere's law to find B. Once you find B, you can find force. Okay, so you use Ampere's law to find B. Let's see if we can do that. So Ampere's law, oh, spoiler, this will end up being the formula. Let's see where that comes from. So let's look at this slide for a second. Here, our task for Ampere's law is to first define, so step one, we have to define an Amperian loop to satisfy the three assumptions. If we cannot find a loop that satisfies these three assumptions, then we're toast. We have no ability at all to use Ampere's law. So let's see if we can. Well, our assumption one is that we have to find a loop that where the B field is constant everywhere along the loop, the theta has to be constant, and we need to know the perimeter of the loop. Those are the three assumptions. So what I've done here is I've drawn a schematic, a slice, a cross-section of this coil, and I'm proposing using a rectangular loop like I've drawn here. Now, you might be thinking to yourself, Mark, the B field is not the same value everywhere along this loop. And you're not wrong, but luckily it's still designed in such a way we can use it. So here, let's look at this. When you integrate BDL, you're integrating each section of your Amperian loop. We did something similar with the parallel plate capacitor. You know where we took a cube, or I guess it was a rectangular prism, for one of the plates of a parallel plate capacitor, and we broke that into 6 faces of the cube. We're going to do something similar here. Although instead of a surface, instead of it being a cube, it's simply just a rectangle. There's no area, right? It's dx. It's a one-dimensional thing. So what we're doing here is we're saying the integral of B dot dl is actually going to be B for side 1, the length of side 1, plus B for side length 2, length side 2, plus B side length 3, length 3, plus B side length 4, length 4. Okay, that is how we are going to use this rectangle. Is when we integrate over the rectangle, we break it into 4 integrals, 4 different sums, because there's 4 parts of the rectangle. So let's look here. Here's a big question, is the B field constant everywhere along the first section of my wire? And I would say yes. In the top section of this, it's not a wire, it's an Amperian loop. The top section of the Amperian loop, is the B field constant everywhere along that top section? The answer is yes. Second question, is the theta value constant everywhere along the top portion of the Amperian loop? Yes, the B field is to the right, the loop is to the right, meaning the theta is 0, it's constant, we're good. Third thing, do we know the length of that side length? Yes, I mean, we're drawing the loop, we know the length, it's L. No problem. So the first sum is simply going to be B times L. Whatever B happens to be, I don't know what B happens to be, that's the goal, but whatever B happens to be, times L, the length of my Amperian loop. Okay, the second one, so this one, that one was 1. Let's do 2 now. 2 is down, maybe I'll do it in blue. 2 is down here. Well, as you see, there is sort of, there are 2 parts to this, right? The first part is exposed to a B field, and the second part is not exposed to a B field. So you're thinking to yourself, Mark, here's a problem. The strength of the B field is not constant everywhere along this path. You're right, it's not. However, we can salvage this because what is the angle between the B field and the Amperian loop? The angle is, we got the B field pointing left, sorry, that's right, the B field pointing right, and we have the path is pointing down. What's the angle between the direction of left and the direction of down? Theta equals 90. So over here, we're actually going to get B as a function of location. I agree with you that it's not constant, because when you're in the loop, there's a non-zero B field. When you're out of the loop, there's no B field. But that variable B field is not a problem because we multiply by cos of 90, right? Don't forget that dot product. So cos of 90 makes this contribution 0. Beautiful. And then the third portion of my Amperian loop, the third portion is down here along the bottom. Is the B field constant everywhere along the bottom part of the Amperian loop? Yes, it's constantly 0. Easy peasy. I love multiplying by 0. So this is simply just going to be 0. And then the fourth part is up here. The fourth part is going to have both the same problem and the same solution as the second part. Part of it will be exposed to the B field. Part of it will be not exposed to the B field. However, that's not a problem because the theta value will be 90. So the fourth one will be B4L cos of 90, and that simply will have a 0 contribution. So we see that this integral, actually this whole integral here, simply just collapses to B inside the solenoid times the length of the coil. Oops, times the length of the coil. Okay, so that's where the left-hand side comes from. Now the right-hand side of Ampere's law is mu naught times the total enclosed current. How much current have we enclosed? Now I'm going to erase my doodles here to make this easier to read. How much current have we enclosed? Well, if we draw our Amperian loop like this, we've enclosed 1, 2, 3, 4, 5 times I. If we draw our loop a little bit bigger, we will encompass N times I. N being the number of loops there are. Here there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 loops. So how much current have we encompassed? 11 times I. Each of these wires carries an I, don't forget. So this is the power of Ampere's law. The power is total enclosed current. Here's where things get trippy for your brain. Let's say there is let me scroll up for a second. Let's say there is 15 amps of current in this wire. That means the power supply or your wall is only having to generate I mean 15 amps is a lot, but your wall is having to generate 15 amps of current. However, using Ampere's law, and if you want to encompass this as your Amperian loop, then you're going to have 15 amps, 15 amps, 15 amps. How many times are you encompassing 15 amps? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe 14, depending how you want to count. So in your math, N is equal to 14. So your total current, I total, is going to equal 14 times 15 amps. This is seemingly mind-blowing because you're able to only put in 15 amps worth of energy, and you can magnify the result of the B field with only one current of 15 amps. You can artificially make it seem like you have 14 times 15 amps, even though your wall outlet only really has to produce 15 amps. Your wall outlet's not actually producing 14 times 15 amps. That's the beautiful part of Ampere's law. So here's the math. The left-hand side collapses to BL, as we've seen. The right-hand side is total enclosed current. So we have I plus I plus I plus I, N times. So now we simply bring down the L to the denominator, and this is how we use Ampere's law to come up with the B field inside of a coil. Okay, well, we have done a lot of material today. So here's a bit of a summary. We've done right-hand rules. We have around 3 of them for magnetism. We have, the thumbs up sign, the good job sign, where you put your thumb in the direction of the current and then you grab the wire with your right hand. We have the physics gangster sign, as they say on Google. And then the alternative to the physics gangster sign is the give me money sign, right? With a flat hand, fingernails in the direction of the B field, the palm of your hand is the direction of the force, and your thumb is in the direction of the velocity or current. We also talked about Gauss's law for magnetism, which is Maxwell's second equation. And this predicts no magnetic monopoles, that it's impossible to have just a north pole or just a south pole, that you always need to have both. And another implication of that is that the magnetic field lines do not have a start and do not have an end. They have to loop around back on themselves. Then we talked about the fundamental magnetic forces, QVB and ILB. I'm noticing now that I'm missing a sign theta in here. We also talked about the trajectory of a moving charged particle in a magnetic field. It's a circular path. This is a result of the cross product between V and B. And you can predict that again using your right-hand rules. Then we talked about the third Maxwell's equation, Ampere's law. And Ampere's law allows us to see, quote unquote, what the source of the magnetic field is. I mean, I use that term loosely because physicists still don't fully understand the magnetic field. We know a lot about it, don't get me wrong. It's just fundamentally there's still some things that are not known there. But we do realize from Ampere's law that it's a moving charge that will cause a magnetic field. So that's kind of a really cool implication. And then using Ampere's law, you can actually solve, oh, there's that weird jumping nature again. Using Ampere's law, we can actually mathematically solve for the B field in a wire as well as a coil. So these two formulas are obtained using, using Ampere's law. We also looked at the formula for a loop, However, this we had to use the Biot-Savart law, which we do not learn about the mathematical derivation of that. It's just I'm letting you know, in case you're Googling, in case you're looking at Khan Academy, if you come across the phrase Biot-Savart law, that's okay. I want you to kind of know why that is and what that's used for, but I will never require you to set up a Biot-Savart law. You just simply have to know what the B field at the center of a single loop is. And the last two things that we covered conceptually is that Ampere's law is used in a very similar fashion to how we use Gauss's law. And specifically, we use Ampere's law as a means to obtain the magnetic force, in the same way we use Gauss's law as a means to obtain an electric force. Okay, we have some time for examples, so let's do a few. Here's one. What is the velocity of a beam of electrons that is shot undeflected, there's the key, undeflected, when moving perpendicular to an electric and magnetic field? E and B are also perpendicular to each other and have magnitudes of who cares and who cares respectively. Also, what is the radius of the orbit if the electric field were to be turned off? So there's sort of two parts here. Part one is what velocity, what's the velocity for, what is it, electron? Yeah, for an electron to go undeflected. Okay, so we've already done an example very similar to this. So I think the example we did before was we knew the speed and we were calculating the strength of the required magnetic field. Here we have E, we have B, and we have to reverse engineer the speed that would require the particle to travel undeflected. So free body diagram. Our goal is to have the electric force and the magnetic force balance. So then we move on to F net equals ma, and in this case, we want the acceleration equal to 0. So we see here that this is going to be the electric force equals the magnetic force. What is the electric force in this case? Well, we have a uniform electric field. So the way you get force from electric field is simply Q times the electric field, so QE. And the magnetic force, is this on a wire? Is this on a particle? Okay, it's a particle. Electron, it's a particle. So it's not ILB, it's QVB. So we can cancel the Q's, and we see here that the required velocity, well, that was easy. The required velocity is going to be the magnitude of the electric field divided by the magnitude of the magnetic field. So all you do is you just divide those two numbers. What's the electric field? The electric field is 7.7 times 10 to the 3 divided by 7.5 times 10 to the minus 3. Now, I don't have a calculator, but 7.7 divided by 7.5 is going to be just a little bit bigger than 1. So this is going to be slightly bigger than 1 times 10 to the 6 meters per second. Okay, so 10 to the 6 meters per second. If you want to compare this just as a point of reference, the speed of light is 3 times 10 to the 8. So this is about 300 times slower than the speed of light. And I say that as if that's a slow-moving thing. It's not. Light is the fastest thing in our universe. Nothing goes faster than the speed of light. There was a math prof, I don't want to name names, but there was a math prof at UTM who did, they have we'll say a friendly feud against physicists, and they tried telling me that nothing goes as fast as the speed of light, and they should have known better to challenge a physicist. And they said nothing goes as fast as the speed of light. I'm like, yes it does. He said, no, you're a physicist. You should know that. That's physics 101. Nothing goes as fast as the speed of light. I'm like, no, light goes as fast as the speed of light. I think what you mean to say is nothing goes faster than the speed of light. And he's like, well, that's just semantics. And I said, well, that's rich coming from a mathematician. You guys are all about nitpicky semantics that really don't mean anything half the time anyway. So I put them in their place, which was kind of funny because mathematicians often make fun of physicists for not abiding by the technicalities. And here was a mathematician trying to make fun of me for abiding by the technicalities. So anyway, so to have the speed of an electron to be 300 times, only 300 times slower than the fastest possible speed in the universe, I think is an incredibly fast speed. Okay, so there's this, part B, sorry, we need part B. Come on. Okay, that gives us some space. So part B says, if we were to turn off the electric field, what would the resulting radius of the electron's orbit be? So of course for part B, oh come on, B, there we go. If we draw our free body diagram again, if we turn off the electric field, right, the electric field is turned off there. If we turn off the electric field, the only force is, oh come on, is the magnetic force. And we know from previous lessons that the trajectory of a charged particle moving in a magnetic field will be circular. So when we write F net equals ma, we know it's going to be a sub c, the centripetal acceleration. So this is going to be mv squared over r equals F net. And looking at my free body diagram, which looks horrendous as now that I'm looking at it, the only force acting on it will be the magnetic force, mv squared over r. So this gets me to qvb equals mv squared over r. One of my speeds cancels. And what were they asking for? They were asking for, what is the radius? So let's solve for radius. Radius equals mv over qb. And I think we've already derived a situation similar to this in a previous example problem. Of course, what is the mass? We're talking about an electron. So this is going to be the mass of an electron and the charge of an electron. So there you go. Yeah, so here, their answer, oh, they're even doing the same thing I'm doing. The real answer was 1.03 times 10 to the 6. And they are saying that's approximately equal to 1 times 10 to the 6. Okay. Here's another one. So for a particle of mass m and charge q moving in a circular path in a magnetic field, show that its kinetic energy is proportional to r squared, meaning the square of the radius of orbit. And then part B is to show that the angular momentum of the particle is qb squared. Or sorry, qbr squared. So we'll do that one later. Let's do part A. What do they want to know? Show that the kinetic energy is proportional to r squared. Okay, don't really know where to start. I know they're asking for kinetic energy. So I'm just going to start by writing out kinetic energy. Okay, so that's 1/2 mv squared. What do we know? The mass of particle m, so we know m. So we know m. Do we know v? No, we don't know v. So that's the problem. We don't know v. Charge q moving in a circular path in a magnetic field. Okay, so we know that it's moving in a circular path in a magnetic field, so we can set that up. So we know qvb is going to equal to mv squared over r. Again, one of the v's cancels, and we're going to end up getting qb equals mv over r. What was the issue again? Oh, right, the issue was v. The issue was we do not have v. So we can solve for v and plug it in. So here, we're going to have 1/2 m. And, oh, right, I got to solve for v first. V is going to equal Q BR over M. So plug that in. I'm going to get Q BR over M squared, right? Because it's 1/2 mv squared. And when I simplify, I'm going to get 1/2 Q squared B squared R squared over M. It's not M squared because this M and one of the M's here will cancel. And there you have it, EK. So here's your kinetic energy, and you see here that EK is proportional to R squared, just as the question asked us to show. Part B, show that its angular momentum is L equals QBR squared. So again, I don't really have a game plan. I know they're asking for angular momentum, so let's just start with the definition of angular momentum. So this is the throwback to Physics 136, which is a prerequisite for this class. If it's a prerequisite for this class, then that means anything in 136 is required, or not required, but could be used and built upon in this class. That's why it's called a prerequisite. So you recall from 136, this is going to be L equals I omega. That's the definition of angular momentum. And the particle that we have here is we have a particle that is traveling, a point particle that is traveling in a circular path around a certain origin point. So the moment of inertia, again, you got to remember what moment of inertia means. There's moment of inertia for a solid disk, a hollow disk, a sphere, a cylinder. If you recall, the moment of inertia for a point particle traveling in a circle around a point is going to be mr squared. That's the moment of inertia of a point particle. Do we know m? Yes. Do we know r? Yes. I mean, it's clearly a function of r. What don't we know? We don't know omega. So again, now you have to remember what omega means. So omega is angular velocity, again, from 136. That's a prerequisite for this class. So we know V equals R omega, which means omega is going to be V over R. So my angular velocity, oh, I should have changed to black. Why didn't it do that? L equals mr squared, and omega is going to be V over R as such. And what is V? We don't know V, but luckily I think we solved for V over here. So when I plug this in, this is going to be mr squared. V is QBR over M, and this R here hangs around still. And we see that the two R's will cancel. We see that the two M's will cancel, and we end up getting, what do we end up getting? We end up getting QBR squared. And I think that is exactly QBR squared. Is that what they wanted us to show? Yes, QBR squared. That's what they wanted us to show. Okay. If we have time, we will come back to this question. We only have 10 minutes left, so I just want to talk about the last topic in this sort of chapter, torque on a loop. And again, the pre-lecture video, that 8-minute video that breezed and sprinted right through a 2-hour lecture's worth of material, they also talked about torque on a loop. Again, without talking about specifics, but they did mention kind of the concepts. So we're going to finish off this chapter by talking about another very useful application to this. And please keep this in mind. We're not just sort of talking about chapters and concepts for the sake of talking about chapters and concepts. You know, just because this is technically true, we're going to teach it to you. That's not how we do things in physics. There are lots of other things in physics that are true. We just choose not to teach you. Because mainly, they're not useful. So who cares? Why bother? This is useful, very useful, and many things in your day-to-day life actually work on this exact principle, where you have current going through a loop in a magnetic field, and it exerts a torque on it, and it turns the loop. That's what we call a DC motor. So there's DC motors everywhere, and because it's very useful to everyday life, we study it and we teach it to you. So don't think we're just doing all this stuff just to bog you down needlessly. You know, we've chosen the curriculum very carefully. Okay, so let's analyze. I'm asserting to you a new idea. The new idea being there will be torque on either a circular loop or a square loop. Now that I've asserted the idea to you, let's analyze why this is going to be true. So whether you have a square loop or you have a circular loop, it doesn't matter. Let's see why there's a current first, or sorry, why there's a torque first. This is an aerial view, a view from the top, bird's eye view, so to speak. If we are known to have a magnetic field in this direction, horizontal parallel magnetic fields in this direction, cool. Now this loop is going to be, let's say it's going to be some sort of square loop. Okay, so we're only seeing the top down, so we're not seeing the square, but please understand that, you know, there is a wire going into the page and a wire coming, looping back around and coming up again. Okay, so if we put manually, if we, like with a battery or with a wall socket, you know, if we force a current through the loop, then it's going to travel in either clockwise or counterclockwise direction. So let's assume the current comes up here and then over this way, and then the current goes down on this side, okay, and then goes down the loop over here, and then, you know, comes back around. Okay, let's assume that's what happens. Well, look at our right hand rules. Conventional current, positive charges, right hand. If you ILB, force equal, the magnetic force equals ILB, the current in the loop times the length of the wire exposed to the magnetic field times B, the magnetic field itself, ILB. Take your right hand, either use your physics gangster sign or your give me money right hand rule. I don't care which one you use. Put your, I'm going to use the give me money one because I like that one better. Put your fingernails in the direction of the B field. So the fingernails in the direction of the B field. The B field on the screen here is turning, or not turning, is headed to the right. So fingernails right. And the current is into the page. You see here the current is X, so it's into the page. So you put your thumb in the direction of in the page, and where does the palm of your right hand face? Down. So you see here there's a blue arrow saying force down. Now interesting, you see the loop itself is on a bit of an angle, but this wire is going into the page. So this section of the wire will feel a force downwards. Okay, now the loop is pivoting on, well, at the center, at the pivot point. Okay, so I mean, if I just scroll up, you know, here's the pivot point. Okay, that's the shaft, so to speak. Okay, so what we've done here is we've said, okay, there is a force this way. This is no different than pushing on a revolving door when you're going into the mall, or pushing on a revolving door when you're going into the student center at UTM, or opening a door to your own house, for instance. Okay, so what you're going to end up getting here is you're going to end up getting a torque due to that force. So torque is defined to be FL sine theta. More specifically, mathematically, if you're concerning yourself with torque mathematically, it is R cross F, or in the context of L, you can use L cross F too. I don't care what symbol you use. That's the mathematical definition of torque. Or if you want to use the algebraic one without calculus, it's just you know, FL sine theta, L being the lever arm. So here, you end up getting, well, let's expand it. What is F? F is the magnetic force on this side number 2 here. What is L? What is the lever arm? Well, the lever arm is half of the width of the loop. If it's a circular loop, I guess that would be half the radius. If it's a square loop, it would be half the width. And then sine theta. Now, I guess I used theta in my equations. I guess the diagram here is using phi, tomato, tomato, same difference. And that's only torque due to one side of the loop. Now let's look at the torque due to the other side of the loop. Here we've got the current coming up. So right hand rule, fingernails again to the right because the B field is to the right. On the left side of the loop, the current is coming out of the page. So tilt your thumb so thumb is pointing out of the board or out of the screen of your computer. And then your right hand rule, the palm of your hand faces upwards. Okay, raise the roof upwards. Bad joke. So that's where this force comes from. Now, if you look at F net equals MA, I agree with you, the net force on the loop is 0. You have F up and F down. The net force on the loop is 0, but torque is not force. Okay, torque is rotation. It's how much rotation the force wants to cause. So the torque due to the side number 2 was clockwise. And well, let me draw that in a different color for you, clockwise. The torque due to side 1 is also clockwise. So they constructively add together to form a nice, smooth, clockwise motion. So the net torque is actually 2 times the individual torque. So you say, you know, torque net is going to be 2 times, and then you see here that the 2's will cancel. So overall, the net torque is simply F magnetic W sine theta. Now, what is F magnetic? F magnetic is going to be ILB, where L itself is the height of the loop or the length. So the width of the loop is one dimension, the height of the loop is another dimension. So if you plug everything in, here we go. There's ILB there. I was getting ahead of myself slightly. If you plug everything in, you're going to get ILB times width times sine theta. Well, what is width times length? Width times length is simply area. So you get the net torque is IAB sine theta, and that's going to be the torque on the loop. Okay, now, just so we're clear, note the theta dependence. There will be orientations where there is no torque that is experienced. For instance, we have the face of the loop is pointing up, right? The normal of the loop is pointing up. If we want to talk about magnetic flux, for instance, no magnetic flux is traveling through the loop in this case. When this is true, let's look at the torque. The force is up on the left, the force is down on the right, and the angle at which they are acting is 90 degrees. This maximizes the torque, right? IL or IAB sine theta. When theta is 90, sine theta is 1. So that maximizes the torque. Similarly, when the face of the loop is parallel to B, or when there's a maximum magnetic flux, then the force is still up, the force is still down, but here the angle is 180 degrees, and sine of 180 is 0. So here there is, not only is it a minimum torque, it's specifically 0 torque. So then you're asking yourself, Mark, if there's 0 torque, how is it a motor? Motors spin. They spin, they spin, they spin, they spin. How is it, you know, if there's 0 torque, how do they spin? Inertia, right? If there's a maximum torque here, then by the time it gets to this orientation, it will be traveling quite fast, or magnitude of speed aside, it will be traveling with a certain speed. So even though there's no torque causing it to continually accelerate, inertia will carry it through the equilibrium point. And as soon as it passes the equilibrium point, all of a sudden there will be a non-zero torque again, and that will keep it going. Okay, I think that's mostly what I was saying here. Yeah, what happens when there's zero torque, inertia, the speed carries it through. And to put this all into perspective, as I mentioned earlier, this is what is called a DC motor. So anything that takes electricity to spin, wow, look how old this slide is. A CD platter. Who uses CDs? Hell, even vinyl. Like records are more common than CD players now. Although DC motors are in record players as well. But honestly, anything that has a spinning motor. The video that we mentioned in the pre-lecture, like your dryer, a drill, literally anything that spins, a fan. You know, when it's getting hot in your house and you turn on the fan, that's a DC motor. DC motors are everywhere, and this is what is powering them. Current in a coil, so you're transforming electrical energy into mechanical energy, right? So we use ILB as a means to create mechanical energy out of electrical energy, and the coupling there is ILB in torque. Okay, so there have been a few problems listed here. In fact, there's only one, and it's fairly easy. The solution is listed there. So, you know, I'll let you review that on your own time. Maybe if we have time on Tuesday, we can come back to it as a refresher before moving on to induction on Tuesday. So, anyway, we finally made it to the end of magnetism. We've done 3 out of the 4 Maxwell's equations. We've done Gauss's law for magnetism, and Ampere's law. So for a first-year life science student in a physics class to have done 3 out of the 4 Maxwell's equations, that is super impressive. So that's where I'm going to leave you for today. And just a reminder, you've got the midterm tomorrow, but you know, that will only be true for this year. So if anyone's watching these videos in the future, that won't apply to you, obviously. So for now, I will leave you, and in terms of YouTube videos, I will see you next week for induction. Ciao for now.